From low Earth orbit, the world below turns to a quiet mosaic. Cities blur into pulses of light, mountains flatten to soft shadows, oceans become a single sheet of breathing blue. Pull back farther and the continents fade. Then the planet itself dwindles to a coin, then to a pale fleck that vanishes in the noise. The farther we step away, the more the details we know slip from our fingers. Now imagine trying to measure the house you live in while trapped in its basement. No door, no window, only hints of rooms above you, a draft under a frame, a vibration through the floor. That is our position inside the Milky Way, observers inside the thing we want to measure. From within this vast disk of stars, dust, and gas, edges are not lines, they are rumors. We cannot walk outside the galaxy to take its portrait, yet the shape that governs our future is a boundary we can barely see. It is drawn by matter that will not shine. It is a shoreline that moves without waves. If we cannot see the edge, can we weigh it? If we cannot draw the outline, can we prove that it exists? If the map is incomplete, are we sure we even live where we think we do? So we turned from pictures to motions. We learned to count the nearest lights by the way they sway against the far background. We learned to time the pulse of certain stars that breathe on regular schedules, brightening and dimming with a rhythm that acts like a ruler. We traced clouds that glow in red, bent by newborn clusters that carve corridors through the gas. Step by step, clue by clue, a dim architecture rises. Yet each meter we add to our ruler reveals a deeper puzzle. The familiar tools begin to slip. The arithmetic refuses to balance. The outer stars move too fast for the light we see. The disk warps where nothing bright enough is present to twist it. Streams of torn stars lace the halo where no river is visible. Are we missing pieces? Or are we misreading the pieces we have? Look up on a clear autumn night and find a faint smear across the north. A quiet almond many nights are too bright to reveal. That is Andromeda, a separate city of stars traveling toward us without sound. Our galaxy and that one already feel each other. There is a chance they're invisible borders. The great halos that hold them overlap right now. If two cities meet before their streets do, when does the encounter begin? If distance and darkness disguise the first touch, how would we recognize it? If the true edge has already crossed the dark between us, do we still speak of separate homes? We step deeper into the basement of our house and place a cup on the floor. It hums. A truck passes on the street above, and the cup quivers. A distant thunder informs the walls. A door bangs somewhere you cannot see, so we learn to read tremors. In the sky, we do the same. We track the sun as it circles the center of the disk, and we note how the whole neighborhood bobs above and below the flat plane like a raft on a long swell. The timescale of that motion dwarfs human history, yet the cycle leaves traces in the vertical motions of stars and gas. A patient listener can hear the floorboards speak. What story do they tell about the weight of the house? What story do they tell about what lies beneath the carpet of light? In everyday language, we measure what we cannot touch by watching how it pushes and pulls on what we can. Gravity is the message. Stars are the messengers. If a star at the outer rim moves as if escorted by a mass that is not shining, we trust the motion more than the view. If a cluster of ancient suns keeps its shape while crossing a tide that should shred it, we update the tide, not the cluster. When patterns repeat across different tracers, across cold gas and hot plasma, across newborn blue and retired red, we set a pin in our map and say, more is here than meets the eye. The map that emerges begins with a disk that is wide rather than thick. The thickness is modest compared to the span. The luminous part, the part that becomes photographs and atlas pages, is a lantern that hangs within a much larger room. That room is the halo, a volume that refuses to light up, except where passing satellites leave scars. Picture a beach at night while the tide is far out. You cannot see the water, yet the sand under your boots darkens. A cool wind lifts from the unseen edge. You hear a hiss where the smallest waves curl around stones. When the halo lifts its voice, it is through paths carved by shredded companions, through speeds that refuse to taper off, through the slight bending of background light. Each whisper adds to a chorus. Each whisper insists that the house is not the size we drew when we first learned the word galaxy. The paradox is stark. The more deeply we sit inside the Milky Way, the less we can photograph it. The more clearly we can weigh it. The view fails us. The numbers do not. The picture is silent. The motion speaks. We accept a method that feels like listening rather than looking. We count the beats of variable stars that act as clocks. We test the pattern speed of the central bar by the way gas streams along it. We trace the compression zones that sweep like slow weather through the spiral. We follow streams of stars, once part of smaller galaxies, as they arc and fold through our sky. Over time, as the measurements stack up, a shape emerges that would look strange if sketched by hand. A disk thickened by flares. A bar that channels gas inward to feed a central engine. A halo that swallows the disk in a sphere of influence many times wider than the bright part we show to children. Stand in a field at midnight, far from traffic and clocks. The Milky Way is not a band across the sky. It is the ceiling of the room we are in. You notice a grain in the light like frost on glass. A mottled texture that tells you the brightness comes from countless points, each too dim to see alone. You feel small. Then you recall that feeling small is a measure of scale, not a verdict on meaning. If the ceiling is this wide, what does that say about our place within it? If our place is a calm spiral lane between busier ones, what does that say about the conditions that let minds ask such questions? If our orbit around the center takes hundreds of millions of years, what does it mean that all of human memory covers only a fraction of a single arc? We face a practical decision that carries a quiet weight. How do we decide where the Milky Way ends? Do we pick the last bright traces of the stellar disk and call that the edge? Do we include the faint fields of stars that float far above and below the plane? Do we include the clouds of cold gas that move with us? Do we include the invisible well of gravity that controls the orbits of dwarf companions and shapes the paths of infalling streams? The answer matters because boundaries guide stories. A small house is a refuge. A large house is a district. A city is a way of life. If our true house includes volumes we never see, the story of who we are changes. The story of where we are going changes. Listen again to the basement. Somewhere, a beam is bearing more weight than the eye suggests. Somewhere, two beams overlap. It is possible that the halos of our galaxy and Andromeda already meet in the dark, a silent handshake far beyond the bright disks. If that is so, we are already members of a larger room, a prelude to a future where two vaults of stars will pass through each other and mix. In that future, most stars do not collide. Space is too wide. But orbits will tilt. The night sky will change. And our descendants will trace new rivers of light. If the first touch already happened in darkness, then the story of our home has already turned its next page. We will not count our way to certainty with a single device or a single method. We will test distances by triangulation where that is possible. We will time stellar clocks where geometry fails. We will fit the rotation curve of the disk, not to make a pretty line, but to test whether the mass we count can carry the speeds we see. We will compare the motions of satellites that skim the edge of the halo. We will follow stellar streams as they wrap the sky and read their bends like handwriting. Each technique makes a claim. Each claim must survive a chorus of others. The house reveals itself when the tales agree. A patient approach brings a second paradox. The better our numbers become, the more alive our map appears. The disk is not a rigid plate. It flexes. It warps. It ripples where past encounters left a memory in the stars. The arms are not frozen wood. They are slow pressure waves that gather gas and let it go. The center is not a still hall. It is a busy engine with a bar that drives lanes of material inward. Even the halo is not empty. It holds strands of stars, faint like cobwebs in a barn, that tell the story of meals our galaxy ate long ago. If the map itself changes, how do we speak of a fixed edge? If the house breathes, when do we say this is the final wall? We can still anchor ourselves to the human scale. Think of leaving your city at night. You pass the well-lit core, glide through quieter neighborhoods, then enter country roads where the light's thin and the road seems to run through fields of dark. You might think the city has ended. A few minutes later, a lonely street appears. A gas station. A cluster of homes on a ridge. Where was the edge? You find that the boundary is not a single gate. It is a gradient. Our galaxy is like that. The stellar neighborhoods thin, yet the traffic of gravity continues. The edge that matters most for orbits lies far beyond the edge that matters for a photograph. At the heart of this mystery sits a simple test. Take a star at a given distance from the center. Ask what speed it needs to keep to maintain its path. Compute the gravitational pull from all the luminous matter you have counted. Compare the needed pull to the observed pull, over and over, across many galaxies. And inside our own where we can, the observed pull is larger. Either our census is missing vast stores of dim mass, or our law of gravity needs a new term in certain regimes. The first answer has built a coherent framework that explains other evidence as well, from the growth of structure to the pattern of light in the oldest radiation we can see across the sky. The second answer remains a live proposal in some corners. Both remind us that a map is an agreement between evidence and imagination. Which agreement will survive the next decade of tests? The hook is not meant to unsettle. It is meant to focus. We choose to treat the Milky Way as a laboratory we inhabit. We will let motions tell us what pictures cannot. We will let streams and ripples reveal the invisible architecture. We will ask not only how large the bright disk is, but how far the sphere of influence extends, how early that sphere met the reach of our neighbor, and what that contact means for the next billion years. We will keep close to real instruments and verifiable patterns. We will test, measure, compare, and follow, because that is how a basement becomes a blueprint. The question is simple. The investigation is not, where exactly does the Milky Way end? Where exactly do we begin? If this lens on scale clicks, like and subscribe to the Quiet Universe channel. It begins with the problem of perspective. From the inside of our galaxy, every direction looks filled with stars. There is no dark horizon to frame where the Milky Way stops and intergalactic space begins. Each patch of sky glows with overlapping patterns of dust and light. We are submerged in the brightness of our own home, trying to map its walls without ever stepping outside. To measure from within is to measure blindfolded. Yet, through patience and indirect reasoning, we have begun to trace the invisible contours of this cosmic house. The first attempts used parallax, the slight shift of nearby stars against the background as Earth moves around the Sun. It is a beautiful trick of geometry. A small angle multiplied by a known baseline yields a distance, the way a surveyor marks the span between trees. For stars within a few thousand light-years, this works perfectly. Beyond that, the angles become too small for ground-based instruments to detect. The Milky Way's dimensions far exceed that limit. So astronomers built better rulers, not longer ones, but smarter ones. Certain stars act as clocks. Cepheid variables pulse with predictable rhythms, their brightness waxing and waning like breathing lanterns. The period of that breathing tells us how bright the star truly is. Compare the true brightness to what we see, and distance falls out of the equation. It was through these stellar clocks that we first measured the scale of our own galaxy, then reached beyond to others. Each pulse was a heartbeat of the cosmos, each interval a step along a staircase of light. But even those steps falter when dust dims the way. Interstellar dust is both veil and clue, scattering blue light more than red, altering what reaches us. Correcting for that dimming requires models of how dust behaves, which themselves depend on knowing the structure of the galaxy. It is a loop, and loops require courage to break. So we turn to radio waves. At those wavelengths, dust becomes transparent, and the galaxy's skeleton appears. Clouds of hydrogen emit a telltale frequency, a line that shifts depending on how fast the gas is moving toward or away from us. The Doppler effect turns velocity into distance when combined with models of rotation. As the signal bends around the disk, we can map spiral arms like sonar in an ocean of gas. The Milky Way ceases to be a blur of stars and becomes a living whirlpool of motion. Still, this is an indirect seeing. We infer structure from motion, brightness from timing, distance from pattern. Every layer of data is both window and distortion. At its core, we are learning to listen rather than look. The sound is light stretched into time, but the rhythm is just as telling. When a wave of star formation sweeps through a spiral arm, clusters of young blue suns ignite together, aging in sequence. By comparing their ages across different parts of the sky, we can deduce the speed at which the arm pattern moves. The arms are not solid bridges. They are slow-moving traffic jams of gravity and gas, places where orbits crowd together and then disperse. It is a choreography measured by echoes, not by sight. The data come from parallax, brightness, radio velocity, and stellar age. Together they build a three-dimensional map that no single instrument could create. Simply put, measuring from the basement means trusting shadows and tremors. Like hearing footsteps on a floor above, we infer the room's size by how the sound spreads. Astronomers use pulsars for this purpose. These dead stars spin with clockwork precision, emitting beams of radio light that sweep the sky. As the waves pass through interstellar gas, they slow slightly, a delay that grows with the amount of material between us and the source. The more delay, the longer the distance. Each pulsar becomes a probe, each signal a ruler made of time itself. By compiling hundreds of such signals, scientists can outline where the interstellar medium thickens, where it thins, and where the edge begins to whisper. Still, there are contradictions. Distances measured by different methods do not always agree. The Parallax catalog from Gaia offers unmatched precision, yet for the farthest stars, tiny errors in calibration multiply into vast uncertainties. Variable stars offer a different yardstick, but depend on assumptions about composition and age. Radio mapping provides geometry, but is bound to models of galactic rotation. Each method claims authority, yet each bends under its own approximations. This tension drives refinement. It is in the disagreement that progress hides. A map too perfect would mean we had stopped testing its edges. To put it another way, we are trapped inside a glowing fog. Every observation travels through layers of distortion before reaching us. Dust bends light, gas refracts signals, magnetic fields twist polarizations. To build a map, we must strip these effects away one by one. Computers model billions of points, each a hypothetical star or cloud, then compare simulated views to the real sky. The best match becomes a provisional truth. The process is iterative, a conversation between data and imagination. Over decades, that conversation has yielded a picture of a barred spiral with several arms, a flat disk about 100,000 light-years across, a central bulge, and a surrounding halo of uncertain depth. Yet every new survey redraws some part of that picture. The walls move, the ceiling tilts, the stairs grow longer. Human-scale comparisons keep this vastness sane. Imagine standing in a windowless basement trying to estimate the building's height by listening to rain on the roof. The rhythm of drops tells you something about distance, about material, even about the shape of the roof. You can make a model, test it with echoes, and refine it with patience. Our instruments do the same. The radar pulses of radio telescopes, the timed blinking of satellites, the precise wobbles recorded by spacecraft all act as echoes of rain in the dark. Over time, the rhythm resolves into structure. What was once a ceiling becomes a dome. Why it matters lies in what we learn about ourselves. By measuring our galaxy, We measure the environment that gave rise to every element we carry. The sun's orbit around the center determines how often it passes through dense regions of gas, where supernovae enrich the medium. The tilt of that orbit may influence the rhythm of comet showers that brush the inner system. The size of the Milky Way's gravitational well dictates how firmly it holds its stars, how long it can recycle its material, how slowly it fades. To know the architecture of the galaxy is to know the blueprint of our own past. Yet the paradox deepens. The more precise our measurements, the more uncertain our boundaries become. The halo of dark matter, unseen but measurable through its pull, stretches far beyond the luminous disk. Where does the Milky Way truly end, and intergalactic space begin? Is the edge the limit of light, or the limit of influence? Every improvement in our tools moves that line outward. The house keeps growing with every new measurement. The basement floor we stand on may not be the foundation at all, but a platform above deeper rooms we have yet to survey. Why it matters again is that the act of measuring forces humility. We are building a map that constantly changes shape under our own corrections. What we call the Milky Way is a conversation between light and time, between what is known and what must be assumed. To measure from the basement is to admit that knowledge can only expand upward, toward a ceiling we may never reach. Each clue we find, each inconsistency we resolve, tightens the weave of a larger pattern. From here, the next question is not just how to measure the house, but how it moves as a single living structure, and what the motion of its parts can tell us about the time it takes for one revolution of our star around its hidden center. The sun moves. It does not hang still in space like a lamp. It sails around the center of the Milky Way, carrying every planet, every comet, every molecule of air that ever entered a lung on Earth. We drift through a tide of gravity, one lap every 250 million years. The last time our solar system was in this region of the galaxy, the continents were still joined as Pangaea. Every breath of wind, every heartbeat, occurs inside that great voyage. The motion is too slow for eyes to see, but it is there, a patient curve written beneath all life. To trace that orbit, astronomers turn to motion itself as a ruler. Every star in the Milky Way follows its own path around the galactic center. Some move nearly circularly, others plunge through the plane in elongated loops. By measuring velocities along the line of sight and across the sky, we can rebuild these invisible paths. The Gaia mission now tracks more than 1 billion stars, timing their positions with exquisite precision. From this flood of motion emerges a portrait of the galaxy as a living system. It is not a flat plate of stars spinning like a wheel, but a crowded ocean where currents weave together and eddies form wherever gravity gathers. In everyday language, this means that what looks like a calm sky is a collection of stars streaming in slow patterns. The sun's path, roughly 26,000 light-years from the galactic center, is neither smooth nor constant. It oscillates above and below the plane, rising a few hundred light-years up, then sinking down again over tens of millions of years. The motion resembles a gentle breathing, a rhythm set by the mass of the disk itself. Stars nearer the center move faster. Those farther out lag behind. Together they create the illusion of steady spiral arms. But those arms are patterns, not objects. They are waves in a sea of orbits. This oscillation is not trivial. Each crossing through the galactic plane exposes the solar system to slightly denser regions of gas and dust. Some scientists have speculated that these crossings could coincide with subtle shifts in comet activity or even mass extinctions. Though evidence remains debated, the thought lingers because it connects celestial rhythm with biological memory. When the solar system drifts upward, we rise toward thinner stellar neighborhoods, cooler cosmic weather. When it sinks, we return to thicker fields, and the sky grows a little busier with dust. Life on Earth may have evolved beneath that long, slow pendulum. We can visualize the orbit as a great racetrack. The sun runs along the inner lane while neighboring stars occupy adjacent paths. around the track. Density waves move like slow ripples. When one catches us, our orbit tightens slightly, then loosens as the wave passes. Over billions of years, the sum of these ripples creates structure rings, bars, streams. The disk is not a still photograph. It is a movie running in geological time. Each revolution rearranges the script a little, shifting the positions of clusters and sculpting new gaps. At its core, an orbit is a negotiation between velocity and gravity. The sun's speed of about 220 kilometers per second balances the inward pull of the galactic mass. If it moved slower, we would fall inward toward the center. If faster, we would drift away into the halo. This balance is delicate, yet enduring. It is the same principle that keeps Earth bound to the sun, but expanded to a grander scale. The orbit defines our place not only in space, but in time. It is a clock with a hand that takes 250 million years to complete one tick. Why it matters is that the orbit ties our history to the galaxy's own. When ancient supernovae enriched the disk with heavier elements, our system was already in motion, passing through those clouds that would later become part of us. Each loop around the center is a sampling of galactic history, a journey through regions that have changed countless times since our star's birth. We are travelers moving through a dynamic ecosystem, not residents of a fixed address. Still, contradictions remain. When astronomers model the Milky Way's rotation curve, they find that the outer stars orbit faster than the visible matter can explain. If only the light we see contributed to gravity, those outer orbits should slow down. They do not. This is the classic clue that most of the galaxy's mass is invisible. To hold the stars in place, something unseen must provide the missing pull. We call it dark matter, not because we understand it, but because it refuses to emit or absorb light. It reveals itself only through its grip on motion. The sun's steady course is proof that this invisible architecture is real. To put it another way, we ride inside a structure built mostly of shadow. Every measured velocity, every plotted path, confirms that the visible stars are only tracers in a deeper web of mass. The halo that surrounds the Milky Way weighs several times more than all its luminous parts combined. The sun's orbit does not cut through empty space, but through that vast, unseen field. Like a ship moving through calm water, we feel the resistance, not by sight, but by the way we stay on course. Over cosmic time, even these graceful paths can warp. The disk itself bends slightly upward on one side and downward on the other, a warp believed to come from interactions with smaller satellite galaxies or from misaligned infalling gas. As we move, we pull on those companions and they pull on us, setting up slow vibrations that take millions of years to settle. This ongoing dialogue shapes the Milky Way's posture. To study the warp is to study the conversation between the main galaxy and its entourage. Each tug is a memory, each oscillation a word. Why it matters again is that these tugs may one day decide our future. The Milky Way does not exist in isolation. Its orbit within the local group is drawing it closer to Andromeda. The dance between the two has already begun invisibly. Their halos may already overlap. The timing of the sun's journey around the center will dictate the view our distant descendants will have when the collision unfolds billions of years from now. The night sky will change, constellations will twist, and the spiral arms will knit into a new form. Understanding our current orbit gives us a way to foresee that distant transformation. In human terms, think of it as living on a carousel that moves so slowly you cannot feel the turn. But every photograph taken centuries apart shows the world outside from a new angle. We are turning, and the scenery of stars drifts behind us. The constellations are not eternal. They are temporary alignments on a rotating canvas. Each epoch inherits a different pattern of lights, unaware that it is part of a single revolution still incomplete. Our orbit also defines time in another sense. As the sun moves through the galaxy, it carries with it a cocoon of influence called the heliosphere, a magnetic bubble that shields us from some cosmic rays. The shape of that bubble changes as we move through varying interstellar environments. In thicker regions, the bubble compresses. In thinner ones, it expands. The very climate of interplanetary space, the background against which the planets live, is modulated by our position along the galactic track. We are children of both sun and galaxy, products of nested cycles. This story, though measured in physics, touches philosophy. The idea that the ground beneath us is in constant motion is humbling. The orbit is not a path we control. It is the frame in which all history unfolds. The Milky Way's clock keeps time for every civilization that will ever rise here. To recognize that motion is to sense our continuity with deep time. The stars we see tonight are fellow travelers, not fixed markers. They are companions on a shared road whose length defies imagination. Somewhere above and below the plane, countless other systems breathe in the same rhythm, rising and falling through the galactic midline. Their combined motion generates the subtle vertical structure of the disk, a thickness that changes with age and composition. Young stars stay close to the plane. Older ones wander farther. The result is a cosmic stratigraphy, a layering of orbits that reveals the history of the galaxy's assembly. Reading that layering is like cutting into tree rings that record not seasons, but epochs. We return then to the sun's journey. Every second it moves 200 kilometers along its orbit. In a human lifetime, it travels only a fraction of 1 degree around the circle. Yet the direction of the galactic center slowly shifts against the background of distant quasars. Instruments must be recalibrated to account for this drift. In the data lies a quiet message. Everything moves, and the axis of our understanding must move with it. The orbit teaches patience. It tells us that position is never permanent, that the meaning of here evolves with motion. To chart that change is to practice a science of endurance. We cannot follow one revolution, but we can measure the traces left by countless past ones. In the end, the orbit around the galaxy is not a path to somewhere else. It is the context of everything we have ever called home. The next step is to look more closely at the engines that shape this motion, the spiral arms that guide star formation and the bar that stirs the inner disk, to understand how these patterns sustain the long breath of the galaxy itself. From the outside, a spiral galaxy appears serene. Its arms sweep outward like ribbons of light, graceful and steady, as though frozen in a moment that never ends. From within, however, that beauty hides motion more intricate than any gear or current on Earth. The spiral arms are not fixed bridges of stars, but moving waves, compressions that travel through the galactic disk like slow weather fronts. They are the conveyors of Starbirth, regions where gravity, gas, and time collide to create new suns. At first glance, one might imagine the Milky Way's arms as physical structures, strings of stars pulled outward by rotation. Yet if that were true, the pattern would quickly unwind. The inner stars orbit faster than the outer ones, and any solid arm would twist apart in only a few 100 million years. What persists instead is a pattern of density, a kind of traffic wave in which stars and gas slow as they enter the arm, crowding together, then speed up as they leave. Each star is like a car in a slow curve, forming a jam that travels even though the drivers continue on. The arm is the jam, not the cars. We detect these patterns through radio observations of hydrogen and carbon monoxide, tracers of the cold gas from which stars form. The data show bright lanes of material compressed by these waves. In the crowded regions, gas clouds collapse under their own gravity, forming clusters of young stars. The process is continuous, repeating as the wave moves through the disk. Once the newborn stars ignite, their radiation and winds push the remaining gas aside, clearing cavities that will later cool and begin again. The arms are thus factories in motion, with assembly lines that never truly stop. In plain terms, the Milky Way makes stars the way oceans make waves. The material moves, but the pattern endures. When one generation of stars finishes forming, Another begins a few light years behind, shifted in phase by the passage of the wave. From above, the spiral appears steady because its machinery runs on timescales far longer than human perception. To live within it is to move through a storm so slow that it feels like stillness. Each arm has its own character. Some carry lanes of hot, ionized gas, glowing in pink light from massive young stars. Others contain cooler filaments rich in dust, visible only in infrared. Between them stretch interarm regions, sparser and calmer, where older stars drift. The pattern rotates at a pattern speed, slower than the rotation of individual stars. At one special radius, the corotation radius, a star moves exactly with the pattern. Inside that zone, the arm overtakes the star. Outside, the star overtakes the arm. The sun is alone near that boundary, in a quiet gap between two major arms. Perhaps that calm has mattered more than we realize, giving life on Earth a stable environment amid the galaxy's turbulence. Astronomers test these ideas using both observation and simulation. When they model the Milky Way as billions of self-gravitating particles, spiral arms appear spontaneously, born from the disk's own instabilities. They are not permanent, but neither are they fleeting. Waves grow, fade, and reform as stars age and supernovae stir the gas. The picture that emerges is one of constant renewal. The galaxy breathes, contracting and expanding in grand, slow rhythm. Why it matters is that these arms dictate where stars like the Sun can be born. The density of gas, the proximity to shock fronts, and the enrichment from earlier generations of supernovae all depend on the local wave. Every element in our bodies was forged in stars that once moved through similar arms billions of years ago. The rhythm of spiral structure is therefore the rhythm of chemical evolution, where arms meet. Matter compresses and complex elements accumulate. Where arms fade, material disperses into the halo, awaiting reuse in future generations. The galaxy is a recycler on a cosmic scale. There is a quiet contradiction here. The arms are both cause and consequence of star formation. They form because gas cools and self-gravity amplifies unevenness. Yet the very stars born in them feed energy back into the gas, reinforcing the pattern that birthed them. Feedback loops like this are familiar in nature. A forest creates its own microclimate. A city alters the weather it endures. Likewise, the Milky Way builds the environment that sustains its architecture. Each explosion of a massive star stirs the gas, seeding turbulence that later condenses elsewhere. The cycle is endless, creative, and destructive at once. To put it another way, the galaxy's arms are like conveyor belts in a vast factory. Clouds enter as raw material, compressed by the traffic ahead. They emerge as clusters of luminous products, then disperse as the line moves on. The conveyor never stops. It does not exist to make any single batch, but to keep the process alive. From this motion comes both continuity and change. Each cluster, each generation is unique, yet all follow the same choreography. Human eyes cannot witness this directly, but we see hints in nearby regions. The Orion Nebula, a cradle of young stars only a few hundred parsecs away, glows as an active assembly line within our local spur. There, the collapse of gas, the ignition of stars, and the feedback of radiation play out in miniature what the entire galaxy performs on a grand scale. The sequence repeats compression, ignition, clearing, rest. If we could speed up cosmic time, the arms would flicker like slow-burning flames, their light pulsing with each cycle of birth and death. The mechanics are elegant. As gas enters an arm, its orbit bends slightly inward due to the increased gravitational pull. This change in direction causes compression, and the gas clouds feel a shockwave. Within those clouds, denser knots form, collapsing under gravity until nuclear fusion begins. The newborn stars then heat their surroundings, erasing the evidence of their birth. They drift forward, leaving the arm behind, while the arm itself continues to move through the disk. In this way, the pattern stays constant, even as its contents change. It is motion without movement, a standing wave in a rotating sea. Why it matters again is that such order in chaos reveals something fundamental about how structure emerges from gravity. The spiral arms are not imposed from outside. They are the natural result of collective motion. Each star, following its own path, unknowingly contributes to a pattern that shapes the lives of billions of others. It is a form of self-organization, written into the laws of motion. Understanding it allows us to see the galaxy not as a static object, but as a living ecosystem sustained by feedback, balance, and rhythm. The arms also guide the flow of interstellar material. Cold gas streams along them toward the inner regions, where the central bar channels it further inward. This transport fuels the galactic center, feeding bursts of activity that may shape the future of the disk. The arms are therefore arteries as well as nurseries. They connect the outskirts with the heart, moving both matter and angular momentum. In a sense, they are the veins of the Milky Way's metabolism, ensuring that material cycles between creation and destruction. At a human scale, the analogy returns us to something familiar. A river's bends create eddies that deposit fertile silt on its inner shores. In those quiet pockets, new growth thrives. Over time, the river shifts, carrying the soil elsewhere, and another patch flourishes. The galaxy behaves much the same. The spiral arms are its fertile banks, and stars are its crops, transient but persistent in their renewal. The calm between the arms is not emptiness, but rest, a fallow field awaiting the next flood of creation. Astronomers still debate how long these patterns last. Some models suggest that the Milky Way's current arms have persisted for hundreds of millions of years. Others propose that they dissolve and reform continually. What remains constant is the underlying mechanism, gravitational interactions among countless moving parts. Whether the pattern is long-lived or transient, it is enough to shape the flow of gas and the distribution of life-bearing elements throughout the disk. Our own sun, older than the present spiral pattern, has likely crossed many such waves, experiencing changing skies as it traveled from one era of the galaxy's rhythm to another. In observing these waves, we learn how galaxies evolve and how they keep forming stars after billions of years. Without the spiral density pattern, gas would settle and cool too quickly, halting star formation long ago. The arms act as a stirring spoon, keeping the mixture alive. They remind us that order and turbulence are partners, not enemies. In the cosmos, the visible beauty of the Milky Way's spirals is therefore a signature of its internal balance, the mark of a system perpetually renewing itself through motion. As we step back from the individual stars and clouds, we begin to see the larger choreography. The disk rotates, the bar turns, the arms ripple outward, and all of it together composes a rhythm that defines the Milky Way's present form. The next question is, how the invisible halo beyond these bright lanes holds this structure together, and what that unseen mass tells us about the forces shaping the galaxy's enduring stability. Far beyond the bright disk of the Milky Way, past the spiraling lanes of dust and the glowing arcs of star formation, lies a region that almost no light escapes from. It does not shine, yet it exerts a powerful hold over everything that does. This is the halo, the ghostly sphere of influence that defines the true scale of our galaxy. To know the Milky Way's edge, we must look not for light, but for gravity's shadow, the silent architecture that holds us all in place. At first, the idea of a halo sounds poetic, like a ring of light. In reality, it is the opposite. It is a vast region of near darkness, extending perhaps 2 million light-years from the galactic center. filled with matter we cannot see. Stars within the disk feel its pull. Dwarf galaxies orbit within it, and streams of stripped stars weave through its emptiness. When we measure the speeds of those orbits, the math refuses to agree with the visible mass. The outer stars move too quickly. The satellites revolve too fast to be bound by starlight alone. Something invisible must add its weight to the scales. The first clues appeared in the mid-20th century, when astronomers charted rotation curves of spiral galaxies. Instead of flattening at the edge where light thins out, the rotation speeds stayed constant, or even rose slightly. To explain this, one could either modify the laws of gravity or accept that most mass is hidden from view. Over time, evidence from galaxy clusters, gravitational lensing, and the cosmic background favored the latter. A new term entered our language: dark matter. In plain terms, dark matter is what makes the galaxy coherent. Without it, the Milky Way would fly apart like sparks from a wheel. The visible stars, gas, and dust make up only a small fraction of the total. The rest is this unseen scaffolding, a diffuse sea of particles that do not emit or absorb light but interact through gravity. They form a nearly spherical halo that encloses the luminous disk. The disk is the visible surface of a deeper structure, much as clouds trace the motion of the air beneath them. Scientists infer the halo's shape by studying stellar streams, the remains of small galaxies torn apart by tidal forces. These streams stretch across the sky in long, curved ribbons. Their paths bend subtly as they move through the halo's gravitational field. By mapping those bends, astronomers can reconstruct the underlying potential. The results show that the halo is roughly spherical but not perfectly smooth. It may be lumpy, rippled by past mergers, and filled with subhalos that once held their own stars before being absorbed. The Milky Way's outer shell is a record of its violent past, an archive written in invisible ink. Why it matters is that the halo defines our true boundary. The luminous disk may span 100,000 light-years, but the halo extends 10 or 20 times farther. It contains the orbits of dwarf companions like the Magellanic Clouds and the Sagittarius Dwarf. It reaches nearly halfway to Andromeda, and may already overlap with its neighbor's halo. If that overlap is real, then the first physical connection between our galaxies has already begun in darkness. The future collision between the Milky Way and Andromeda would not be a sudden encounter, but the final act of a merger that started long ago, hidden within the shared reach of their halos. At its core, the halo also hosts the oldest remnants of the galaxy's history. Ancient globular clusters, dense spheres of stars older than the disk itself, orbit far above the plane. Their distribution reveals the scale of the gravitational well. Some clusters travel hundreds of thousands of light-years from the center before falling back again. Their motion tells us how deep the well is, and by extension, how much unseen matter must reside there. Through these wandering fossils, we weigh the invisible. To put it another way, the halo is both cradle and cage. It is the environment that allowed the Milky Way to grow by gathering smaller systems, and the force that now restrains them from drifting away. Each satellite galaxy moves within its grasp, stripped of stars and gas as it spirals inward. Streams like the one from the Sagittarius Dwarf trace luminous scars across the sky, looping around the disk in graceful arcs. These streams are evidence that the halo is not empty space, but an active participant in shaping the galaxy's form. The composition of dark matter remains unknown. It could be exotic particles that barely interact with normal matter, or a more subtle modification to gravity itself. The search is ongoing through detectors buried underground and telescopes that look for subtle distortions in starlight. None have yet confirmed what the halo is made of, but all agree it must exist. Its presence is unavoidable in every calculation. It bends light from distant galaxies, slows the expansion of the universe locally, and binds stars that should otherwise escape. The unseen outweighs the seen by an order of magnitude. Why it matters again is that understanding the halo may reveal not only the structure of our galaxy, but the composition of the universe itself. If dark matter is a new kind of particle, it would mark one of the greatest discoveries in physics, a window into the earliest moments after the Big Bang. If, instead, gravity behaves differently on large scales, then the halo becomes a clue to rewriting the laws that have guided science for centuries. Either way, the implications reach far beyond the Milky Way. The halo is a frontier between what we can measure and what we can imagine. In human terms, picture standing in a city at night. The streetlights and windows define the limits of sight, but the city's influence stretches much farther. Roads continue into suburbs and open fields. Invisible but real. People, goods, and signals flow through that darkness, connecting the bright core with unseen edges. The halo is that infrastructure for the galaxy. It connects the visible disk with the cosmic web beyond, linking our home to the greater structure of the universe. Without it, the lights would scatter and fade. Within this vast, unseen sphere lies a thin population of stars known as the stellar halo. These are relics of past mergers, stars torn from their original systems, and now drifting in orbits tilted far from the plane. They act as markers in a near-empty sea. Surveys like Gaia have traced their paths, revealing streams and shells that correspond to ancient collisions. Each structure tells a story of assembly, of how the Milky Way grew from smaller fragments. The smooth halo we once imagined is instead a complex mosaic, stitched together by gravity over billions of years. The halo also interacts with the intergalactic medium, drawing in a slow rain of gas from cosmic filaments. That inflow replenishes the disk, feeding future generations of stars. Without it, star formation would have ceased long ago. The halo is therefore not only a container, but a supplier, funneling material inward, while allowing energy and radiation to leak outward. It mediates the galaxy's exchange with its environment, like a porous membrane around a living cell. As we measure its reach, we realize that the halo is far larger than we ever imagined. Its faint glow of scattered X-rays and gamma rays hints at hot gas filling enormous volumes. If we could see in those wavelengths, the Milky Way would appear as a sphere rather than a spiral, a vast globe of tenuous plasma with a bright disk suspended inside it like a candle in mist. The true galaxy, then, is not a flat spiral at all, but a layered structure of light and shadow. This perspective changes our sense of place. The stars we see on a clear night are the thin crust of a much larger body, our Sun, orbiting midway between center and edge, swims within the halo's gravity like a fish in deep water. We are not bound to the surface, but suspended within a volume. The idea redefines the meaning of above and below. Everywhere we look, the halo extends, silent yet present, shaping the paths of stars, bending the motion of galaxies, and perhaps seeding the next cosmic generation. If we could see the halo, it would not appear as a glowing dome, but as a faint shimmer at the edge of perception, a whisper of density where space thickens. Its beauty lies in absence. The halo teaches us that what is unseen can still define reality, that the invisible framework of gravity is more enduring than the light it holds. Our understanding of the Milky Way, and of ourselves within it, depends on accepting that most of what exists does not need to shine to be real. The next step is to descend from this invisible sphere back into the luminous machinery of the disk, to study the warped and twisted structures near the center that reveal how gravity's hidden hand shapes the forms we can finally see. When we picture a galaxy, we often imagine a perfect spiral viewed from above, symmetrical and calm. Yet the Milky Way is not a flawless disk. It bends. It twists. It ripples like a sheet of metal struck by an unseen hammer. Its central regions are not flat, but dominated by a bar, a dense structure of stars that stretches across the core, stirring gas into curved lanes. These distortions are not cosmetic flaws. They are signatures of motion and memory, hints of the forces that drive our galaxy from within. The Milky Way's symmetry is an illusion, and the engine that powers it is hidden in plain sight. The warp of the galactic disk was first revealed through radio observations of hydrogen gas. Astronomers found that beyond the Sun's orbit, the disk tilts upward on one side and downward on the other, giving the galaxy a subtle S shape when viewed edge-on. The stars follow this curve, bending in concert with the gas. The cause, long debated, appears to be a combination of internal dynamics and external influence. Nearby satellite galaxies tug on the outer regions, while the gravitational pull of the dark halo and misaligned streams of infalling gas twist the plane. The warp is not static. It vibrates slowly, like a bell rung eons ago, whose tone still echoes across the sky. At its core, the bar represents a different kind of order. It is a dense rod of stars about 27,000 light-years long, aligned roughly with the disk, but rotating as a single unit. The bar acts as a gravitational lever, funneling gas inward along curved orbits. As the material spirals closer to the center, it piles up in a ring where new stars are born at a rapid pace. This inward flow also feeds the supermassive black hole at the heart of the galaxy, a quiet giant that occasionally awakens in bursts of energy. The bar is therefore not just a shape, but a mechanism, transferring angular momentum and driving evolution from the inside out. In everyday language, the Milky Way's bar is like a spoon stirring cream into coffee. It takes the rotational energy of the disk and redistributes it, blending material from different regions. As gas moves inward, its potential energy converts to heat, fueling both star formation and the quiet rumble of the galactic nucleus. The process shapes everything we see. Without the bar's influence, the inner spiral arms would lack their present symmetry, and the center would remain less active. With it, the galaxy breathes, cycling matter between the core and the outskirts. The hidden engine behind all this is gravity responding to imbalance. Whenever mass accumulates slightly off-center, it amplifies its own pull, gathering more material until a new structure forms. The bar likely arose from such an instability a few billion years ago, when the inner disk became dense enough for stars to collectively influence one another's orbits. Once formed, the bar began to rotate and to drive waves outward through the disk. Those waves interact with the spiral arms, reinforcing or disrupting them depending on timing. The result is a living architecture, one that shifts and reforms over immense spans of time. Why it matters is that these distortions tell us how galaxies evolve. The warp and bar are not unique to the Milky Way. They appear in many spirals across the universe. Their presence marks a transitional stage between youthful chaos and mature stability. In younger galaxies, mergers and uneven gas flows dominate. In older ones, internal resonances like bars take control, reorganizing the remaining material. By studying our own galaxy's warp and bar, we are reading its autobiography in motion. Still, contradictions persist. Some models predict that the bar should slow down over time as it transfers angular momentum to the halo, yet observations suggest it is rotating faster than expected. Either our understanding of the interaction between disk and halo is incomplete, or some unseen process is sustaining the speed. The warp, too, presents puzzles. It may precess, its line of nodes shifting with time, yet measurements disagree on the rate. The galaxy behaves like a complex instrument whose strings vibrate in multiple modes, each influencing the others. To put it another way, we are living on a disk that hums. Every orbit of the Sun is a trace across that resonance. The gas in the outer regions rises and falls like the edge of a drum, while the bar at the center beats a slower rhythm, sending waves that travel outward. The combined result is a symphony of motion, inaudible, yet measurable. Astronomers can model these waves numerically, watching the disk flex and breathe. The patterns resemble ripples on a pond disturbed by multiple stones, overlapping and creating temporary nodes of calm and tension. At a human scale, one might compare this to the mechanics of a city. The downtown bar is the main thoroughfare, drawing traffic inward, while the outskirts rise and fall with slower rhythms. Over time, the city adjusts to its own momentum, building new roads and tearing down old ones. The Milky Way behaves much the same, though its timescales are millions of years long. The warp is the bending of a skyline, the bar the grid of motion beneath it, both products of constant negotiation between structure and change. Why it matters again is that our location within this system shapes everything about the environment in which we live. The Sun's orbit takes it slightly above and below the warped midplane, meaning that our view of the sky changes subtly over millions of years. The density of gas, the background radiation, and even the influx of cosmic particles vary with this motion. These changes are tiny on human scales, but profound over geological epochs. The engine that stirs the galaxy also stirs the conditions for life. Observations from infrared surveys have refined our understanding of the central bar. It appears to twist at its ends, linking to the inner spiral arms. The pattern speed of this rotation sets up resonances that trap stars in elongated orbits, creating a peanut-shaped bulge when seen from certain angles. This bulge, too, tells of past motion, likely shaped by the bar buckling vertically before settling again. The center of the Milky Way is not static. It is a churn of old and young stars, gas clouds colliding, and magnetic fields threading through. The warp, bar, and bulge together form the beating heart of a dynamic organism. We have learned that the Milky Way is flexible. It bends without breaking, adjusts without losing coherence. The forces that distort it also preserve it. The warp shows how the outer regions respond to external tugs. The bar shows how the inner regions manage their own momentum. Together, they keep the galaxy in balance, a self-correcting system sustained by feedback between light and dark, motion and rest. If the halo provides the skeleton, the bar and warp provide the muscles and sinews. They are the mechanisms that convert potential into motion, stillness into form. Every atom in our world has passed through these cycles, once part of gas drawn inward by the bar, later thrown outward by supernova winds, then caught again in the slow rise of the warped plane. Our lives unfold within this endless exchange between order and turbulence. The mystery remains: what is the ultimate driver of this motion? Is it the gravitational influence of the dark halo, or the legacy of ancient collisions, or an inherent instability in rotating disks? The answer may be all of these at once, an interplay of internal and external forces. In seeking that answer, we are not only describing the Milky Way's structure, but probing the fundamental behavior of matter under the rule of gravity. The next chapter will lead us outward again, to the boundary where the galaxy's appetite becomes visible, where the halo feeds on smaller companions and rivers of stars stretch across the sky, revealing how the Milky Way continues to grow even now. The Milky Way is not a polite neighbor. It has grown by consuming others. Around its outer rim, faint trails of stars mark the remains of smaller galaxies torn apart by gravity. These stellar streams curve like ribbons across the sky, each one a scar from an ancient meal. They tell a simple truth about how galaxies evolve. They grow by merger, by collision, and by slow, quiet cannibalism. The edge of our galaxy is not a boundary at all, but a feeding ground where tides stretch and mix the light of once independent systems. Astronomers first glimpsed this process when they mapped the Sagittarius dwarf galaxy, a small companion that passes through the Milky Way's outer regions. Its stars form a long arc that wraps nearly halfway around the sky. The dwarf itself is mostly gone, absorbed by the greater gravity of our home. Similar streams, fainter and older, wind through the halo like ghostly veins. Each one records a moment when the Milky Way's pull overcame the self-gravity of a smaller system. Over billions of years, this slow devouring has built much of the stellar halo, enriching it with debris from countless forgotten galaxies. To understand how such cannibalism works, imagine a small moon circling a planet. At a certain distance, the difference in gravity between the near and far sides of the moon begins to tear it apart. This is called a tidal limit. In a galaxy, The same principle applies. When a dwarf passes close to the Milky Way's center, the difference in gravitational pull across its span becomes extreme. Stars begin to drift away, following curved paths that trace the orbit of the victim. Over time, those stars stretch into a stream, a line of light marking the path of destruction. In everyday language, these streams are like crumbs on a tablecloth, revealing the trail of a meal already eaten. By tracking their motion, astronomers can reconstruct not only the orbits of the destroyed galaxies, but also the shape of the Milky Way's gravitational field. The streams act as test particles, their curves showing where the potential deepens and where it flattens. In this way, the galaxy's violence becomes our measuring tool. What it tears apart helps us see what holds it together. One of the most detailed examples is the Sagittarius stream, a loop of stars thousands of light years wide. It passes above and below the galactic plane, forming a vast figure 8 around the sky. The path reveals that the Milky Way's halo is not perfectly spherical, but slightly elongated. Other streams, such as GD1 and Orphan, show similar distortions, suggesting that the dark matter halo is lumpy rather than smooth. These lumps may be the cores of other subhalos, dark satellites without stars, the echoes of galaxies that never quite formed. The Milky Way is surrounded by the ghosts of things it consumed and of things that never fully came alive. Why it matters is that this process of slow merger is still happening. The Magellanic Clouds, two bright smudges visible from the southern hemisphere, are not permanent satellites. They are falling toward the Milky Way, trailed by long streams of hydrogen gas. In a few billion years, they too will be stripped and folded into our halo. Each merger brings new stars, new elements, and new energy to the system. The Milky Way grows heavier, its structure changes, and the rhythm of star formation shifts. The cannibalism that built it continues quietly, just beyond the reach of our eyes. To put it another way, galaxies live by recycling others. There is no clean separation between creation and destruction. The stars pulled from a victim eventually join the disk, enriching it with metals and dust that become seeds for new generations of suns and planets. The universe conserves nothing static. Everything is traded, repurposed, and reborn. Even the Milky Way itself is not exempt. In time, it too will be absorbed, merging with Andromeda to form a still larger system. The eater will be eaten. The evidence of past meals is everywhere, once you know how to look. Some streams appear as faint overdensities of stars against the field, others as gentle ripples in velocity space detected by precise surveys. Gaia's data have revealed dozens of these remnants, some as large as entire constellations, others barely perceptible. Each carries a unique fingerprint of chemical composition, allowing astronomers to match stars that once belonged together. The result is a forensic reconstruction of the galaxy's diet, a cosmic autopsy where every shard tells a story of survival and loss. Why it matters again is that these discoveries redefine our understanding of what a galaxy is. It is not a static island of stars, but a dynamic ecosystem where accretion and disruption never end. The boundaries between galaxies are temporary, drawn by gravity and erased by time. The Milky Way's smooth appearance from afar hides a turbulent history of assimilation. To see it clearly is to accept that stability in the cosmos is an illusion. Everything we think of as whole was once assembled from fragments. Some of the streams have revealed surprises. Certain stars move faster or slower than models predict, suggesting the influence of invisible masses within the halo. These perturbations may be caused by small clumps of dark matter, predicted by theory but unseen by telescopes. If confirmed, they would offer the first direct evidence for dark substructure in our galaxy. Thus, the debris of old galaxies becomes a tool for probing the unseen. The faintest ribbons of starlight may carry clues to the nature of matter itself. Human-scale analogies help us grasp this slow violence. Picture a mountain stream eroding rock over ages, carving valleys and depositing layers of sediment. Each flood rearranges the landscape, And the river you see today is both destroyer and builder. The Milky Way behaves the same way. Its gravitational current grinds smaller systems into dust, spreading that dust across the sky, where it coalesces again into new stars. The cycle of ruin and creation is the natural rhythm of galactic life. In the distant future, as the Milky Way continues to consume its neighbors, the halo will become denser, and the disk may thicken with the debris. The shape of the galaxy will change slowly, its spiral pattern blurring into an ellipse. This is not death, but transformation. Galaxies evolve by eating. And through that hunger, they sustain the universe's structure. Every light we see in the night sky is the result of such exchange, a record of energy passed from one system to another. The act of cosmic cannibalism also provides context for our own origins. The elements that built Earth were forged in stars from many ancestral galaxies. Some of those stars were born here. Others began their lives in systems long since digested by the Milky Way. Our solar system is literally a product of mergers, a mosaic of matter gathered from countless sources. The edge of the galaxy, where such mergers occur, is not distant in meaning. It is part of our lineage. Each new survey extends this lineage further. Instruments like the Vera Rubin Observatory will soon detect even fainter streams, tracing the outer halo in exquisite detail. We may find that what we call the Milky Way is only one node in a network of interacting systems, each feeding the next. The quiet cannibalism of galaxies ensures that the cosmos remains a place of continual renewal. Stars die, galaxies merge, and yet the grand structure persists, always reshaping itself. At the edge of our galaxy, where the visible fades into darkness, the boundary blurs between victim and host. Here, the Milky Way's hunger meets the cosmic web that feeds it. The halo drinks from those filaments, drawing new material even as it consumes the old. The outermost stars are already mixed with the outskirts of Andromeda's domain. The feast that began billions of years ago is still underway, and through it, the universe writes its story of endless transformation. The next step leads us forward in time, toward the inevitable meeting of giants, when the Milky Way and Andromeda draw close enough for their disks to intertwine, and our night sky becomes the stage for the slowest collision ever seen. Every night, rising quietly in the northern sky, a faint oval of light hovers between the stars of Cassiopeia and Pegasus. To the unaided eye, it looks like a small cloud, barely visible unless the night is dark and clear. That ghostly glow is the Andromeda Galaxy, the nearest major spiral to our own, and the largest member of the local group. What seems calm from this distance hides a slow inevitability. Our two galaxies are not drifting apart, but drawing closer together, pulled by a mutual gravity that ignores the vast emptiness between them. In a few billion years, they will merge. The Milky Way and Andromeda are already bound, moving toward a confluence that will reshape the night sky and the structure of both systems forever. This approach is not a violent charge, but a patient embrace. The current separation is about 2.5 million light-years, and the closing speed is around 110 kilometers per second. At that pace, it will take roughly 4 billion years before the disks begin to overlap. On human timescales, that seems eternal. But in the chronology of galaxies, it is soon. They have been approaching since before the Earth cooled enough to form oceans. The first living cells arose under a sky already committed to this future union. The evidence of their motion is written in light. Astronomers measure Andromeda's velocity by the slight compression of its spectral lines, a blue shift that reveals its movement toward us. Most galaxies beyond the local group show a red shift, receding with the expansion of the universe, but Andromeda is an exception. Its gravity and ours have overcome cosmic expansion, binding us together in a local domain where attraction wins over drift. That gravitational handshake will eventually tighten until both galaxies fall into each other's arms. In everyday language, it is as if two cities drifting on an ocean current are slowly converging, their lights brightening as they near. At first, their outer suburbs, small satellite galaxies and halos, touch. Later, their main roads, the disks, begin to mingle. Eventually, their cores align, and the skyline of each becomes part of the other. The process will unfold over billions of years, almost invisible from one generation to the next, yet transforming everything. At its core, the merger will not be an explosion of collisions, but a graceful rearrangement. The space between stars is so immense that even when the galaxies overlap, individual stars will rarely collide. Instead, gravity will stretch their orbits, scattering some outward into long tails and drawing others inward toward the center. Gas clouds, however, will interact. As they compress and collide, they will ignite bursts of star formation, brilliant but short-lived seasons of creation. The night skies of any surviving worlds will fill with unfamiliar constellations, vast arcs of light, and glowing clouds of newborn stars. Why it matters is that this event will mark the next major transformation in our cosmic neighborhood. The merger will create a single elliptical or lenticular galaxy, sometimes called Milkomeda, though names will mean little by then. The combined system will be larger and more massive than either of its parents. With a calmer shape and slower star formation, the spiral structure that defines both galaxies will fade, replaced by a smoother, more spheroidal glow. Over time, the remnant will settle into equilibrium, orbiting around a new common center where two supermassive black holes now exist. These central black holes, one in each galaxy, will spiral toward each other as gravitational waves carry away energy. When they finally merge, they will release a burst of gravitational radiation that ripples across the universe. The event will occur long after humanity has changed beyond recognition or vanished entirely, but its echoes will persist. It will be the largest gravitational wave our local group will ever produce, a reminder that even at the scale of galaxies, gravity unites what it once kept apart. The first sign that the merger has begun will be a shift in the pattern of the Milky Way's satellites. The Magellanic Clouds and other small companions will fall toward the merging pair, caught in the growing well of their shared gravity. Streams of stars will stretch between the two galaxies, forming luminous bridges. The halos that already overlap will blend completely, creating a common envelope of dark matter that binds everything inside. From within our solar system, the sky will show Andromeda growing brighter year by year, its disk widening until it becomes a rival to the Milky Way's own band. To put it another way, the night sky of the far future will become a theater of slow motion, millions of years before contact. Andromeda will appear as a majestic spiral spanning a significant portion of the heavens. As the galaxies draw together, the view will turn surreal. Constellations will distort. Familiar stars will seem to drift as the geometry of the sky changes. When the disks begin to overlap, enormous arcs of star formation will blaze in ultraviolet and blue. For a brief time, measured in tens of millions of years, the night will glow brighter than at any point in the Milky Way's history. Why it matters again is that this merger illustrates the long arc of cosmic evolution. Galaxies are not static islands. They are dynamic entities shaped by encounters. Every large galaxy we observe carries scars of similar events. The Milky Way's halo is already built from earlier mergers, and Andromeda shows evidence of having consumed several smaller galaxies. The Coming Confluence is not a new phenomenon, but the latest act in a long drama. Through it, matter will continue to recycle, gravity will continue to sculpt, and the universe will continue its patient work of transformation. The aftermath will be strangely peaceful. Once the orbits settle, the combined galaxy will contain fewer young stars but an abundance of older ones. The dense gas that fueled star formation will largely be spent or heated beyond condensation. The result will be a reddish, quiescent system glowing with the combined light of hundreds of billions of ancient suns. For any observers still orbiting a surviving star, the sky will be both emptier and grander, a glowing sphere of light where once there were two separate spirals. From a human perspective, the thought of our galaxy colliding with another evokes both awe and vulnerability. It is a reminder that even the largest structures we know are transient. The Milky Way, as we see it today, is a fleeting arrangement, destined to merge, change, and fade into a new form. Yet this impermanence is not tragedy. It is the way the universe sustains complexity. Each merger spreads elements, reshuffles orbits, and gives rise to new patterns. Creation is built on the ruins of earlier forms. Astronomers can already simulate the event. In their models, the first pass will fling long tidal tails of stars into space. The second pass will tighten the merger, and after several oscillations, the galaxies will fuse into one, the Sun. By then, we'll have completed many more orbits around the center. It may find itself in a new region of the merged system, perhaps farther from the center, perhaps cast into the outer halo. The planets, if they remain, will witness skies of unimaginable beauty, the last light of two galaxies blending together. Somewhere deep in the future, the merged system will look out upon a darker universe. By then, cosmic expansion will have carried distant galaxies beyond our horizon. The merged Milky Way and Andromeda will be alone, drifting through space with their satellite galaxies as the only visible company. The local group will have become a single, self-contained world island, glowing quietly amid the deepening night. In that solitude lies a final meaning. The Coming Confluence is both an ending and a beginning. It ends the separate histories of two galaxies, but it begins the story of a new one, a synthesis greater than its parts. The forces that draw them together are the same that hold every atom in place, the same that shaped stars, planets, and life itself. To witness the idea of this merger is to glimpse the unity of cosmic history, where attraction triumphs over distance, and where the slowest collision becomes the most beautiful. The next and final act will turn inward again, reflecting on what this vast evolution reveals about meaning, impermanence, and the fragile awareness that lets us see the universe measuring itself. Beyond the edges of our galaxy, past the local stars and the faint halo of dark matter, lies a structure so immense that even our largest maps can capture only fragments of it. The Milky Way is not alone in space. It resides on one filament of a grand cosmic web, a network of galaxies and gas stretched across billions of light years. These filaments, stitched together by gravity, define the architecture of the visible universe. Every cluster, every void, every star that has ever shone occupies a position in this vast and delicate lace. The roads that connect us to the rest of creation are not paved with dust or gas, but with the invisible threads of matter itself. The discovery of this structure began with surveys that charted the positions of thousands, then millions, of galaxies. When plotted in 3 dimensions, they revealed that galaxies do not fill space evenly. Instead, they form walls, filaments, and nodes surrounding immense empty regions called voids. These filaments are hundreds of millions of light years long and only a few million light years thick. They connect clusters like neural pathways in a brain, or the filigree of frost on a window. Within those threads flow the materials that feed galaxies, sustain star formation, and shape the evolution of cosmic time. In everyday language, imagine the universe as a sponge, its dense strands holding all the water while vast empty spaces lie between. We live within one of those strands, inside a node where several filaments converge. The local group of galaxies, which includes the Milky Way and Andromeda, sits in a small spur of this web connected to the larger Virgo supercluster. Gravity acts as the sculptor, pulling matter along these filaments into knots of higher density. Over billions of years, the web has grown more defined as galaxies merge and gas drains toward the centers of clusters. At its core, the cosmic web is a reflection of the earliest conditions after the Big Bang. Tiny fluctuations in density within the primordial plasma expanded and stretched, forming the seeds of later structure. Dark matter, which dominates the universe's mass, provided the scaffolding. Ordinary matter followed its gravitational blueprint, cooling and condensing into stars and galaxies along the densest lines. The filaments we see today are the frozen fingerprints of those first fluctuations, amplified by cosmic expansion. Why it matters is that the web gives context to everything else. The Milky Way's halo, its cannibalized neighbors, even its future merger with Andromeda, all occur inside this larger network. Our galaxy is one strand within a cluster, and that cluster one node in a structure that extends beyond imagination. The web determines how galaxies grow, how they spin, and where new ones can form. It sets the rhythm of cosmic evolution, linking the fate of the smallest planet to the largest void. To map this hidden architecture, astronomers use light as a probe. They measure how the radiation from distant quasars is absorbed by gas along the line of sight. Each absorption line corresponds to a filament of hydrogen stretched across intergalactic space. These observations create a three-dimensional portrait of the cosmic web, revealing rivers of matter flowing between galaxies. Computer simulations confirm the pattern, showing gas streaming through filaments into clusters where it is heated and compressed, lighting up in X-rays. The universe behaves like a circulatory system, with the cosmic web as its network of arteries. In plain terms, galaxies are the bright intersections where the traffic of matter slows enough to settle. The filaments are the roads. Gas travels along them, feeding clusters, while dark matter provides the invisible scaffolding that holds it all together. Between these filaments lie the voids, vast expanses with densities a fraction of the cosmic average. They are the quiet deserts between cities, expanding faster than the dense regions and shaping the overall geometry of the universe. The cosmic web is not static. It evolves as gravity continues its work. Filaments thicken, nodes grow denser, and voids expand. Over time, small structures fall into larger ones, merging to form superclusters. Eventually, gravity will isolate these massive regions as the expansion of the universe accelerates, pushing distant filaments beyond our view. The map of the future universe will be simpler. A few bright islands floating in an ocean of darkness. Even now, that process has begun. Galaxies not gravitationally bound to us are receding faster than light can travel, disappearing from observation forever. Why it matters again is that this realization defines the scope of our cosmic horizon. The local group will remain intact, but the greater web will fade from reach. The threads that now connect us to the Virgo cluster and beyond will stretch until they vanish. For future observers, the universe will appear small and lonely, stripped of its network. The cosmic web we see today is a fleeting privilege of our time, a view that will not last forever. The web also reveals the deep unity of physics. The same laws that govern the orbit of a planet also shape the structure of the universe. Gravity is the common language, weaving scales from the human to the galactic. Each filament is the sum of countless individual motions. Just as a river is made of drops, to study it is to glimpse the pattern behind complexity, the order hidden within apparent chaos. The web's geometry even influences the cosmic microwave background, imprinting subtle anisotropies that trace its growth across time. At a human scale, we can think of the cosmic web as the root system of existence. Every galaxy is a leaf drawing nourishment from this unseen soil. The flow of matter along filaments sustains the formation of stars and planets, and therefore the possibility of life. When we look up at the Milky Way, we are seeing only a local branch of a much larger organism. The light that crosses our sky is the whisper of currents flowing through that immense lattice. The intergalactic medium, filling these filaments, is not entirely dark. It emits faint radiation, mostly in X-rays and ultraviolet, detectable only with the most sensitive instruments. This diffuse gas holds most of the universe's ordinary matter, more than all the stars combined. Its temperature ranges from millions of degrees near clusters to only a few thousand in the outer filaments. These are the reservoirs that feed galaxies. When a filament channels gas into a cluster, it compresses and shocks, glowing briefly before cooling and sinking inward. The cycle repeats, maintaining the cosmic balance between expansion and condensation. To put it another way, the universe breathes through these threads. Matter flows inward, Energy flows outward, and together they maintain a dynamic equilibrium. The pattern is fractal, repeating at different scales. Molecular clouds feed stars, spiral arms feed galactic centers, and filaments feed clusters. Each level reflects the same principle of connectivity. The web is both structure and process, form and motion intertwine. The cosmic web also acts as a kind of memory. Its filaments preserve the paths along which matter traveled since the earliest times. By tracing them, scientists can reconstruct the story of cosmic assembly, how gravity turned uniform gas into the rich diversity of galaxies we see today. These threads are the footprints of creation, the roads along which the universe walked toward complexity. Standing on Earth, orbiting an ordinary star in a peripheral arm of the Milky Way, we occupy one tiny crossing in that web. Yet through observation, mathematics, and imagination, we can follow the roads outward to scales that dwarf comprehension. The realization carries both humility and wonder. We are not at the center, but we are part of the pattern. The atoms that make us once flowed along these same filaments, guided by the same gravity that now keeps our feet on the ground. As the story of the Milky Way unfolds within this network, we see that our galaxy's growth, its halo, its bar, its future collision, all are local expressions of the web's broader design. The same gravitational rivers that shaped the first galaxies still flow through us, unbroken. Our home is not an isolated island, but a node in an endless fabric that stretches across time itself. The next act will turn inward one final time, leaving behind the architecture of matter to explore the meaning it reveals, the mirror it holds to consciousness, and the quiet question that lingers when the maps end but the mystery remains. The farther we travel through the cosmos, the more the map turns inward. Every orbit, every filament, every halo we have traced leads to a question not about where we are, but what it means to be here at all. The Milky Way, immense and restless, is not only a place in space, but a moment in time, a phase in the universe's unfolding story. Its stars are clocks, its light a record of change. To understand it is to understand impermanence written in starlight. We live inside a structure that will not last. The spiral arms will fade, the disk will thicken, the halo will blend with Andromeda's, and the cosmic web will stretch beyond sight. Yet for a brief span, in this thin interval of cosmic history, the universe allows itself to be seen. We are witnesses occupying a rare window when the lights are still on and the pattern is still visible. The darkness that surrounds us is not emptiness but anticipation, a reminder that all radiance is temporary. At its core, the universe is a process of becoming, not a static stage. Stars form, shine, and die. Galaxies merge and dissolve. Even space itself expands and cools. The grandeur lies not in permanence, but in the continuity of change. Matter that burns in a star today will drift as dust tomorrow and rise again in another form. Every element that shapes our world was once inside another star. We are living evidence that the universe recycles its own memory into thought. To put it another way, consciousness is the galaxy learning to look back at itself. The atoms in our eyes were forged in the cores of ancient suns. Now they are used to measure the very stars that made them. When we speak of the Milky Way's age or size, we are the galaxy measuring its own dimensions through us. The act of understanding becomes part of the thing understood. The observer and the observed are not separate. They are different aspects of the same unfolding story. Why it matters is that this realization restores a kind of humility. For centuries, humanity imagined itself at the center of things. Then we learned we were on a small planet around an average star in a spiral arm of a larger galaxy. Now we know that even that galaxy is one thread in a vast web. The loss of centrality might seem like diminishment, yet it brings clarity. We are not the purpose of the cosmos, but we are one of its ways of knowing itself. That knowledge is not small. It is the mirror by which the universe sees its own reflection. In everyday language, we could say the stars are our teachers. They show us that beauty comes from process, not perfection. A nebula is messy because creation is ongoing. A spiral arm is temporary because order is alive. The universe is not a completed design, but an unfinished experiment. And we are participants, not spectators. Our task is to look, to listen, and to keep the measure honest. When astronomers measure distance or age, they deal with light that has traveled for millions or billions of years. To observe a galaxy is to look into its past. That delay means we never see the universe as it is, only as it was. The present moment of the cosmos is always just out of reach. In that sense, the universe teaches patience. It tells us that understanding requires time, and time requires acceptance of delay. The philosophical echo of all this is simple yet profound meaning does not come from scale, but from connection. A grain of sand contains the same laws that shape the largest clusters. The pattern that forms a galaxy also forms the spiral of a shell. When we trace those parallels, we glimpse coherence, a harmony that transcends size. The same physics that holds a planet in orbit holds our hearts in rhythm. The same gravity that curves light curves the arc of our understanding. Every civilization that gazes upward eventually confronts the same dual truth: the universe is vast beyond comprehension, and yet the mind is vast enough to imagine it. That symmetry is the quiet triumph of awareness. We cannot conquer the cosmos, but we can map it in thought. We cannot halt entropy, but we can recognize its beauty. The measure of a species may not be what it builds, but what it can contemplate without despair. Our future lies within a cosmic solitude. When the merger with Andromeda completes and distant galaxies fade beyond the reach of light, our descendants, if any remain, will see only the merged glow of a single system. The rest of the universe will have slipped over the horizon of time. The night sky will seem smaller. Yet within that smaller view will remain the same questions, the same desire to understand. The end of visibility will not be the end of wonder. In that far future, perhaps a new form of life will rise around another star. Look into the faint halo of a reddish sky and ask where it came from. It will find traces of the Milky Way and Andromeda in the elements of its own body. And in doing so, will rediscover the same truth: to exist is to be part of a cycle that began before memory and will continue after meaning fades. Awareness is temporary, but significance is cumulative. Every act of observation adds to the universe's self-portrait. At its core, our search among the stars is a search for continuity. We long to see patterns that outlast us because they remind us that we belong to something larger. Yet the deeper the search goes, the clearer it becomes that transience itself is the pattern. Galaxies are born and dissolve, light travels and dims, lives begin and end. The only constant is the unfolding itself. Perhaps that is enough. Standing under the night sky, we are surrounded by light that has crossed unimaginable distances to reach us. Each photon carries the record of a journey, a message that says, "I was there, and now I am here." To receive that message is to participate in the same movement. Every glance upward closes the circuit between the cosmos and the consciousness that observes it. In that exchange, something wordless passes between matter and mind. It is not knowledge alone, but reverence, the awareness that seeing itself is sacred. The universe may be silent, but its silence is not empty. It is the stillness before meaning, the pause between creation and recognition. Within that quiet, everything that has ever existed continues to echo. The Milky Way's light, the pulse of distant quasars, the soft radiation left from the beginning. All of it forms a chorus that never truly ends, only changes tone. Our task is to listen, to look at the night not for answers, but for participation. The more we learn, the more we realize that the act of questioning is the universe thinking through us. The mystery does not shrink as we explain. It deepens. because explanation reveals new layers of ignorance. Understanding is not the closure of wonder, but its renewal. So we return to the image of the galaxy seen from afar, its arms faint and beautiful, its heart glowing quietly. It is not aware that it is being seen, yet within one of its spiral lanes, awareness has emerged to see. The eye that observes the galaxy is itself a product of the galaxy. The circle closes. Light meets light. In that meeting lies the deepest symmetry of all. Somewhere beyond the edge of everything visible, the cosmic web continues to stretch. Filaments drift farther apart, carrying the memory of connection into the expanding dark. And here, on a small world orbiting an unremarkable star, we watch, we measure, we remember. The act of witnessing becomes a kind of creation, the translation of silence into meaning. If the universe is indeed a story still being written, then consciousness is its punctuation, the pause that lets the sentence breathe before it begins again. We do not yet know how the story ends, or whether it ends at all. But perhaps the truest question left for us is not where we are going, but what it means that the universe has learned, even for a moment, to look back at itself.